Okie dokie, folks. So, continuing on with how to count, one of my favorite topics personally, going on to this thing called permutations here. Uh, so, starting off with a definition, suppose you want to put things from a list of items in a certain order. That's what a permutation is. So, in this example here, we have 7 coats, and we're going to put 2 of them onto hangers. Now the order here matters. That's what makes it a permutation. If the order doesn't matter, we're going to see that in the next video. That's called a combination. But for now, the order actually does matter, which in a sense actually makes it a little bit easier. Okay, so scenario. You have 2 hangers here, and you have 7 shirts to hang. You got a red one, a blue one, a rainbow one, and so on. Okay, now the question is, how many possible ways could we do this? Again, the order here matters. So if I put the red shirt on the first one, and then say the purple one, or this magenta one, I guess, on the second one, that would count as 1 right there. But if I switch the order, so let's suppose I label these, this is the first, and this is the second hanger. If I switch the order in my closet and put the red one over here and the purple one over here, we would count this as a second permutation. Okay, so I'm gonna give you a minute here, or pause the video and think, how many ways could I do this? Okay, so you've had a minute to think about that, or several, of course. Here's one way to think about it, and we're going to use the idea of two counting principles that we used yesterday. Because think about what you're doing. What we're doing is we're looking for the number of ways to do what? Well, we're thinking of the number of ways to put the first coat, or maybe so I'll say hang the first coat, and then that's important, and then thinking myself enough space here, and then hang a second one, right? If that's the case, how do we deal with this and then thing? Is that and then gives you a hint. It says, well, you first figure out how many ways to hang that first one, and you multiply. That's where that part comes in. Then you hang the second one. Right. Okay, so before you've done anything, how many ways are there to hang a first coat or use that first hanger? Well, it doesn't matter. The hanger fits every single coat as far as we're concerned. And so really, the question is, how many shirts are, or how many coats are there at the beginning? So at the beginning, we start off with 7. And after I've hung that first one, how many are left? Well, there's just 6 left, and so there'd just be 6. And that would just be 42 ways. This accounts for the order mattering. Okay, so by doing this, doing 7 ways to hang the first one, multiplying that by the 6 ways to hang the remaining 6, that already takes care of the fact that red blue is different than blue red, or red purple is different than purple red. This already accounts for that. Okay, again, if the order did not matter, then red blue and then blue red, that would be considered the same thing in the same type of list, and we would have to account for that. Again, that will come up in the next video of combinations. Okay, these slots are often, a lot of people use these slots, and I use them still, and I will use them in the next one, is to just think of it as the slots are the hangers. So this is like hanger number 1, and then the second slot here is hanger number 2. Okay, so we go on to now 3 hangers. Well, what changes? So we still have 7 coats. Let's not forget that. if I have 7 coats and 3 hangers, well, I'll draw my 3 hangers. This would be kind of the shortcut way to do that. This hanger 1, 2, 3. But we still think of it the same way, right? First, you're putting your kind of number of ways to do, or to use hanger 1 times the number of ways to use hanger 2 times the number of ways to use hanger 3. Ready? Before you use anything, you have 7 coats to hang up. After you've hung up the first one, now you have a second one, or sorry, now you only have 6 left. And then after those 2, you only have 5 left. All this together, that'd be, what is that? 210 different ways. Okay. The number of ways is, another way to say this is 210 permutations. Right here. Okie dokie. Slightly different question now is that, let's suppose we still are going with this scenario. We have 3 hangers, still the 7 coats, and still one of each color, a rainbow, a green, and so on. What is the probability that one of the shirts is green now? Again, think about this, but just remember that that if we want probability, we have to figure out the number of ways of the particular event versus divide by the number of ways in our sample space, or number of outcomes in our sample space. Okay, so pause the video here and try this one on your own first. Okay, the sample space is usually easier, and often because it's in a multi-part problem, you've probably already done it. In this case, let's put this over here. My sample space is really just the number of ways to use the 3 hangers. We've already done that. That was right here. Okay, and so in this case, our sample space is 210, or the number of outcomes in our sample space. So I'll write that right there. Okay, now we just have to figure out. Now again, the event is usually just a more specific example, or a more specific instance of that sample space. So in this case, we want to figure out how many ways are there to use 3 hangers, but with the additional condition that the green shirt is used, or green coat. Okay. Here's the way to think about it, and I'm going to go back to the slots here. Let's pretend, now the green coat has to go somewhere, right? So I'm just going to pretend that the green coat goes right here. Okay. Now, there's only one green coat in all my 7 coats here. So how many ways are there to use that one slot here for this first hanger? There's really only one way. Okay. If I've used that green one right there, I still ask this, it's a similar question. How many are there to use on the other 2? Well, on the second one, there's 6 left. And then on the third one, there's 5 left. Multiply all those together and you'll get 30. Right? Okay. But I should pay attention is that I don't care which of the, I say shirts and coats, sorry about that. There's no reason that the green shirt or the green coat has to go on that first hanger. It could go on the second one, it could go on the third one as well, right? And so if I draw it out, the green one could go right there. That's the green one. In which case I have 6 left here and then 5 left there. Or, again, you could go, you put the green coat on the third hanger. In either case, there's 30 different ways for each of those 3 scenarios. Now, the fact that we used or, and I'm running out of space here, I apologize. The fact that we use or means to add these ones all up. And so the number of ways in our event space, my probability is equal to 30 plus 30 plus 30, which would be 90, divided by the total ways to use 3 hangers, or hang 3 coats, over 210, which we simplify this down, should come out to what? 9 over 21, which is 3 over 7. So if you hang 3 shirts at random, again, we have 7 different colored shirts, and they're all different. The probability that at least that you've used the green one in one of those 3 slots, it's going to be 3/7, which is almost half. Okay. Let's do a couple more examples here. Oops. So the reason I just want to show us this example is because you'll see this type of problem pretty often, is that suppose you have the letters in this name here, Kaylee. We'll call a word, quote unquote, just a string of letters. It doesn't have to be an actual English word in the dictionary. Example, I could use one word using those letters, would be Y-I-K-A. Okay, so the question is, how many 4-letter words could be made using the letters from Kaylee's name? The context changes, and maybe like the way it looks is different than the coats and the hangers, but it's really the same thing. In this case, if we want to use an analogy to what we have been talking about, is how many hangers do you have? There's 4 hangers. 4, and then how many coats are there? Well, there's 1, 2, 3, 4, 5, 6. 4, 6 coats. In this case, the coats are all different, which is helpful as well. We want to pay attention to that. Okay. This is where the slots really just helps me. So I'll either draw the 4 slots here, or my 4 hangers, quote unquote. Well, how many options are there for each one? I'm putting 1 letter into the first one, and then the next one, and then the next one, and then the next one. And so that first option, for that first slot, there's 6, that first letter in the word. There's 5 letters left to pick from, and then 4, and then 3. And this comes out to 6. I'm not sure what that comes out to, but we won't worry about that right now. Well, okay, that's it. So it's 30 times 12, which is 3,600. Oh, sorry. 360. Okay. Last one here is how many 6-letter words could be made? Again, very, very similar. We'll draw our 6 slots for our letters. Again, kind of like Hangman, actually. And there's 6 options for there. Then 5, 4, 3, 2, and then 1. You'll notice here that this actually just comes out to 6 factorial. If you were thinking factorial from the very, very beginning, that's pretty interesting, because I'm multiplying 6 times 4 times 5 times 3. Sorry, 6, 5, 4, 3. As we count down, that's a little bit like 6 factorial, right? But not entirely, because 6 factorial would be equal to 6, 5, 4, 3, 2, 1. And so I could rewrite the answer to this one, using factorials. Now, if I just use 6 factorial, that's obviously not right? Because I need to get rid of that 2 and the 1 on the bottom. And so if I write this out like so, 5, 4, 3, 2, 1. I need to get rid of that 2 and that 1. So one way to do that would be to divide that whole thing by 2 times 1. Leaving you with 6 factorial divided by 2 factorial. In this scenario down here, where we have 6 letters, sorry, 6-letter words from 6 letters, that'd just be like saying 6 factorial over 0 factorial. And we haven't talked quite about this, but let's think about this 0 factorial business. It seems weird because we're so used to saying like 1 factorial is equal to 1. So what would 0 factorial equal? Well, think about this. How many 6-letter words can be made using the letters from Kaylee? That's 6 factorial. I think that's fair. My question to you now, let's erase this here, is how many ways to, let's say a 4-letter word from 4 different letters. Doesn't matter what they are. You would do the same thing that you just did, right? And so I would create 4 slots. 1, 2, 3, 4. 4, 3, 2, 1, which is 4 factorial, right? So another way to say factorial, or another way to describe factorial, over here, n factorial is equal to the number of ways to, create a list of n objects, again, where order matters. Again, the order is very important here. Okay. And we can see that from here. So there's 6 factorial is the number of ways I could rearrange 6 letters. 4 factorial is the number of ways I could arrange 4 letters. So here's kind of the weird way, and this might start some arguments, is that 0 factorial, if we follow the same line of reasoning, is that 0 factorial is the number of ways create a list of 0 objects. Right? Okay, ready? I'm going to do all the ways to do that. Boom. That's one way. Now again, that's where the weird part comes in, and some people might be mad with this, is that the one way to rearrange 0 objects is to not do anything. But that itself is still one way. And so this is where we're going to have to deal with this scenario, is that 0 factorial is actually equal to 1. Okay. There's several other ways to explain why 0 factorial equals 1. One way is based on a bunch of patterns. We won't get into that right now. If you want to talk about it, you can always email me and so on. Okay. The reason I want to bring this up is because this will fit into our formula here, is that how can you arrange a group of R things from a set of N things? Again, so let's just I'm just trying to generalize this process here. The R things is a group, the R things here is the number of hangers in our analogy. Oops. The N things here is the number of coats or shirts or whatever it was. And so you have N things to pick from, but you can actually only use R of them. And again, the order matters. This part here is very important. if we think back to, so why don't you actually pause here and see if you can come up with a little formula for this. Okay, so if we go back to this part right here with Kaylee using the 6 letters from Kaylee to create a 4-letter word, we look at it, the top part came out with 6 factorial, and we can actually also see that with the coats here. With the 7 coats, it started off with 7, 6, 7, 6, 5. That's the start of 7 factorial, right? But we didn't go all the way to 7 factorial. We stopped at 5, right? And then we didn't use 4, 3, 2, 1. If we go back to example with the words, we started off with 6 factorial, 6, 5, 4, 3. But we did not use 2 and 1. And that's why we divided by 2 factorial down here. We'll use this now to say that the 6 factorial was the number of options you had, the number of coats. And so if the number of coats is n, then we have n factorial first up top. And then here's the question is, how do we figure out where to stop? Now here, we stopped at 2, and, oh sorry, up here, we lost the 2 and the 1, right? We didn't want to use that. And then we divided by 2 and the 1. It's factorial over here. If we notice here, when we were only using 1, 2, 3 hangers, this would have ended up being 7 factorial over 4 factorial. So what's the connection here? Or we're looking for the connection between the 7 coats and the 3 hangers, and there being this 4 factorial. And over here, looking at the connection between Kaylee, 4 letters, and then the 2 factorial. You might be able to notice here that that 2 is just the difference between the number of letters available and the number of letters you're actually using, or the 4 being the difference between the number of coats available and the number of hangers. And so the factorial that goes on the bottom here is just that difference, n minus r factorial. Now, we should just be aware here that this scenario only makes sense if the number of things you're picking from is equal to or greater than the list that you're building. Because if you only have 10 things and you're trying to build a list of 100 things, the answer, that's impossible because you don't have enough things. Another way to write this is NPR, where the N and R are little subscripts. That's just another fancy way to write it, but we don't really have to worry about that. You would just say the number of ways to do this is n factorial or n minus r factorial. Alrighty. This video is dragging on a little bit long, so I'm just going to end it there, and then we're going to look at this example right here in the next one.